So what is simple harmonic motion? You just imagine the motion of a particle in uniform circular motion. Okay? So we first start with remembering this topic, UCM. I think you all remember what is UCM? Uniform circular motion. Why it is called uniform? Because in this uniform circular motion, the angular velocity will remain the same. What is angular velocity here? Omega equal to 2 pi by time period. What is time period there? Particle starts from A and comes back to the point A with uniform velocity. Then time required is called the time period, and 2 pi by time period is the angular velocity. Omega equal to 2 pi by t we know. And 1 by t stands for what? Frequency. We refer frequency in this chapter as f, small f. You can write n also, no problem. You write n. So omega going to be equal to 2 pi n. In uniform circular motion, the position of the particle changes continually. Direction of velocity also changes. But magnitude of velocity will remain the same. If you say that velocity v1 here, v2 here, then that mod v1 equal to mod v2. You must remember it, that you consider v, and accordingly we go for derivation of centripetal force. But here we are not going to discuss what is centripetal force. Our aim is to discuss about simple harmonic motion. Why have I started example from simple harmonic motion? That you have to understand. From uniform circular motion, that you have to understand. In this uniform circular motion, we can find motion of another particle here. Just consider circular motion on this circle where a particle starts its motion from the point A. This is the vertical diameter. This is vertical diameter here. On this vertical diameter, we draw a perpendicular from every position of the particle in UCM. So this is our vertical direction, vertical diameter, B, O, B dash. You can take this one as horizontal diameter. Okay, A, O, A dash. This one is the horizontal diameter. And this is the vertical diameter. B, O, B dash is the vertical diameter. When the particle is situated at the point P, let us draw a perpendicular from this point to the vertical diameter. PM be the perpendicular. So M is the foot of perpendicular. And particle goes from A to P after time t, that with angular velocity omega, which we have already defined, and we are telling this one is uniform circular motion. Now from the next point, from next position of the particle, you draw another perpendicular. P1 M1 is the other perpendicular. At the point B, when it reaches, you won't be able to draw any perpendicular because it reaches at the extreme point and the point coincides with the extremity of the vertical diameter. Perpendicular drawing not possible. But as soon as particle reaches here at this point, again you can draw perpendiculars. Isn't it? Particle going from first quadrant to second quadrant, draw perpendiculars, draw perpendicular here also, perpendicular here also, draw perpendicular here. So why am I drawing all these perpendiculars? What is the purpose of it? If you see that motion of the particle from A to B, foot of perpendicular goes from O to B. In this UCM, we draw perpendiculars on vertical diameter. We can do it on horizontal diameter also. From every position of the particle. Then what do you observe? The particle goes from A to B. Particle in UCM goes from A to B. A to B. And where does the foot of perpendicular goes? The foot of perpendicular goes from O to B. Okay? Then what happens? Particle goes from B to A dash. I mean second quadrant it covers. What is the result here? The foot of perpendicular goes from B to O. Make the observation this way. Particle goes from A dash to B dash, foot of perpendicular. This one goes from O to B dash. Particle goes from B dash to A, foot of perpendicular, I am writing FOP, foot of perpendicular goes from B dash to O. Okay? So, a particle in UCM has described a complete circular path. The foot of perpendicular has described one complete to and fro motion about the point O. Agree or not? It goes from O to B, then B to O, then O to B dash, then from B dash to O. So started from O, comes back to O, foot of perpendicular. Particle starts from A, comes back to the point A. This to and fro motion of the particle has a very important characteristic. Let us study it first, then I will give you the definition of the topic you are going to learn today. What is the speciality about this motion? Particle in UCM, foot of perpendicular, completing a to and fro motion. What is the speciality in this motion? Let me explain. So we try to draw the circle of same radius here. This is the circle. Particle in UCM. Just this time we take the vertical diameter. We have taken it as BOB dash. Particle starts from here, A, goes to the point P. P is arbitrary, anywhere. This happens in time T. Okay? So this angle we can measure. Omega be the angular velocity in UCM. Then particle goes from here, the particle goes from A to P after time t. Then particle goes from A to P after time t. This arc length it has described. We are going to discuss the motion of foot of perpendicular. Where does the foot of perpendicular goes? Foot of perpendicular goes from where to where? Foot of perpendicular goes from O to M. So we can say that displacement of the foot of perpendicular, therefore displacement of foot of perpendicular is what? That is OM. OM is what? Y. In the diagram, Y by A is what? If this angle is theta, you can see that this one going to be theta, alternate angle. So Y by A going to be sine theta. Agree or not? The perpendicular by the hypotenuse is Y by A sine theta. So what is Y over there? Therefore, Y equal to A sine theta is what? You know, omega equal to theta by t. This will give us theta equal to omega into t. So this is what? This is actually displacement of FOP, foot of perpendicular after time t. Before we go for actual definition of the topic we are doing today, let me tell you something about this equation which we have just got. Displacement of foot of perpendicular is y equal to A sine omega t. Since y equal to A sine omega t, we differentiate with respect to t. What do I get if we differentiate with respect to t? If we differentiate with respect to t, then dy by dt will be A omega sine omega t. One minus cos square omega t. So this thing I am discussing. First, you know, this has become dy by dt, that velocity of particle equal to A omega sine omega t. This is velocity of foot of perpendicular is this. Then what is the acceleration of foot of perpendicular? Acceleration of foot of perpendicular, if we take this one as v, that is going to be dv by dt. Agree or not? dv by dt is what? d dt of A omega. Sine omega t is wrong because sine derivative is cos. Okay, and I write the rule here. d dx of A sine bx plus c AB cos bx plus c. So remember that when you differentiate, the coefficient of x comes out. Okay, this actually you have done in the beginning of class 11. I just remind you. This is the rule of derivative. So when you differentiate that expression, that ddt of A omega cos omega t, what do you get? Same way cos omega t differentiation we have to do. This will give us A omega outside minus sine omega t into omega. So we write acceleration. I told you in the beginning that acceleration will use different symbol because A stands for amplitude here. We take F for acceleration and big F for force in this chapter throughout. So acceleration F is equal to minus omega square A sine omega t. What do you observe here? Minus omega square A sine omega t. The equation we have started with y equal to A sine omega t. Now we got it back here. It is becoming minus omega square A sine omega t minus omega square into y. But y stands for what? Displacement of foot of perpendicular. Y is displacement of foot of perpendicular. Therefore, acceleration of the foot of perpendicular is proportional to displacement. Now, let me tell you something more about this. Acceleration of foot of perpendicular, we have proved, is proportional to displacement. Now, this circle, we'll refer this one as circle of reference. In this circle of reference, we had taken this one as the vertical diameter, BOB dashed. And the foot of perpendicular goes from O to M after time t, this we have taken Y. Now, what I am doing there, for simplicity of our calculation or to study the motion properly, I am taking this projection of the diameter on horizontal direction. This is BOB dashed. This part is our M, which we have taken as Y here. Okay? Y is the displacement. So particle going away from it. What is the direction of motion of the particle? This way. With what velocity? That we have seen, V equal to A omega cos omega t, and F is what? Minus omega square Y. So don't you think that if particle goes this way, the acceleration of the particle, acceleration on the particle is directed towards the mean position. I mean towards the center of circle. Now forget about the circle. Just the circle of reference. You just remember this special type of motion where acceleration is proportional to displacement and directed towards the rest position. This is the rest position. Particle started from here, no? This was center of circle. This we can refer as mean position. Mean position is here. This is mean position. So particle going towards right with some velocity, but acceleration is directed towards the mean position. This special type of motion will be referred as simple harmonic motion. Okay? So this definition we got here, SHM I am defining. Now, the to and fro motion of the particle in which acceleration is proportional. So SHM is defined as the oscillatory motion or to and fro motion, of a particle in which acceleration is proportional to displacement and directed towards the mean position is called simple harmonic motion. What is the equation of particle in SHM? Y equal to A sin omega t. But this definition has come later. Initially, photoperpendicular motion. So, uniform circular motion is linked with this, because see, in the equation of simple harmonic motion, omega is there. Omega is there. Omega we borrow from where? From uniform circular motion. So, in uniform circular motion, if we consider the projection of the particle on vertical diameter, then motion is simple harmonic. Okay? So, we first define simple harmonic motion as the projection of another definition. Circle of reference already I told. What is that definition? That is the projection of UCM on the vertical diameter is SHM. And SHM's specialty is this one. Equation will be in this form and acceleration will be proportional to displacement. But the question is it only on vertical diameter? I am writing or horizontal diameter. Why? Then equation going to be changed. If we take the circle of reference, this is called circle of reference, then this is vertical diameter and this one is the horizontal diameter. From particle's position, if you draw perpendicular here, PL is the perpendicular. Okay, this is A, O, A dash. And displacement always is considered from here. We take this one as X. Okay. Then we can find the value of X also. Why? How? We have taken OL. OL is displacement after time t. Particle goes from A to P after time t. X is the displacement. Why do you say displacement? Particle goes from A to P. So displacement we must say from A. No. We will always refer displacement from the point O. Okay? Because here particle going to execute simple harmonic motion this manner. A to O to A dash, then A dash to O, then O to A, then like this. That's why we take OL as X. This one A remains the same, this one theta remains the same. Theta is what? Omega t. So X by A going to be cos theta. Therefore, X equal to A cos omega t. So this is also equation of simple harmonic motion. Okay? X equal to A cos omega t also. So together this thing, X equal to A cos omega t and Y equal to A sin omega t both represent equation of particle in SHM. For time t equal to 0, what do you observe? X is A, particle at the extreme position here. Okay? At the point A only, because O to A distance is A over there. And at time t equal to 0, Y is what? No foot of perpendicular drawn, the particle will remain at the point O only at time t equal to 0. So both will represent equation of motion of a particle in simple harmonic motion. In both the motion, acceleration is proportional to displacement. Okay? and directed towards the mean position. Now, we just remember this circle of reference always based on this and taking the equation of SHM y equal to A sin omega t we have taken, say I am taking y equal to A sin omega t. This is B O B dash, just for symmetry we keep it here, particle at the point M after time t. This we have already taken, and we have taken y, this one. We also have calculated velocity, that is dy by dt, which is given by A omega cos omega t, and acceleration, this is velocity. F is the acceleration, which is given by minus omega square into y. Minus indicates that it will be directed towards the mean position. Now, let us discuss the position, the oscillation here. Particle going from, say, O towards B. Then, velocity of particle gradually increasing or decreasing. That we have to discuss. Acceleration increasing or decreasing. That also we have to discuss. It is better to start with this value of acceleration. What do you observe acceleration? Minus omega square y. So if the particle goes away from the point O, y increases, so F increases. Means acceleration directed towards mean position increases. So then we discuss with time y increases. So acceleration directed towards the mean position also increases, isn't it? Now, in the circle of reference, a radius of circle we have taken A. Radius we have taken A. This B was one extremity. It cannot go beyond B because on the circle we are considering projection, it cannot go beyond B. So in the equation of SHM, y equal to A sin omega t, y stands for what? Displacement of particle. A stands for what? Maximum displacement. This is called amplitude. So we write this one first. Amplitude. Amplitude is A. It is the maximum displacement from it is the maximum displacement on either side of the mean position. It is the maximum displacement on either side of the mean position. Okay, this is called amplitude. So amplitude is A. Now, with time y increases, so acceleration directed towards mean position also increases. Maximum acceleration will be what? Maximum acceleration is obtained when y equal to A. So if max, you put y equal to A over there, it is going to be omega square A. This F max occurs where? This F max occurs either on the right extreme or on the left extreme. This is the maximum acceleration, omega square into A. But we haven't mentioned about velocity. Let's see what happens for velocity. Now, V is what? A omega cos omega t. This we can write A omega 1 minus sine square omega t. Okay? Now, Y is what? A sine omega t. So, sine omega t is Y by A. You put it there. So, V is omega root over. This will help us to study the simple harmonic motion properly. Look at these two expressions. The expression for acceleration, it was F equal to minus omega square y, and expression for velocity, omega root over a square minus y square. You have stated that maximum acceleration is obtained when y equal to a and f max is omega square into a. But when y equal to a, what happens to velocity? Put y equal to a over there. Omega root over a square minus a square. This is equal to 0. But y equal to a is where? Y equal to a is at the extreme position. So, what is happening there? You are saying that it is maximum displacement on either side. All these you have stated about acceleration. Now, what happened to velocity? With time, y increases. So, what about the velocity of v? V decreases. Am I correct? So, this we can comment over there. From here, with time, y increases. As a result, v decreases, and v becomes 0 at both the extreme, on the right as well as on the left. This happens at the extreme position. Agree or not? This happened at the extreme position. V equal to 0. At the extreme position, acceleration is maximum at the extreme position. So, what is actually happening there in SHM? Once more, try to pay attention here. This part is RB and this is B dash. Particle going this way. Displacement is y. What is happening there? Its acceleration, which is directed towards the mean position, F is increasing, because F is minus omega square y. Y increases, F increases. But V is what? Omega root over a square minus y square. So V decreases. Particle goes from O to B. So during its journey from O to B, F increases and V decreases. At the extreme position, what happens? At the extreme position, V becomes 0 and A becomes maximum, omega square A. And if you consider the sign, it is minus omega square A. So what will happen? When it reaches at the point P, what is your prediction about particles motion? Does it stop over there? When you have studied in motion on straight line, there is a question: can a particle have maximum acceleration or acceleration without velocity? Teachers told you that yes, it is possible in simple harmonic motion. At the extreme position, particle has acceleration but without velocity. But that acceleration is negative. So what will happen? At the extreme position, the particle turns back. So as a result, the particle turns back. Then what will happen? You always remember the expression that F minus omega square y and V equal to omega root over a square minus y square. Why the particle turns back? In your mind it will play that it is due to acceleration directed towards the mean position. That's why it will turn back. And when it goes towards O, the value of y decreases. Now we consider journey from B to O. Journey from B to O. What do you observe? Journey from B to O. What is happening? Y stands for what? Y stands for displacement from the mean position. B to O, y decreases. Y decreases with time. So y decreases with time. What do you observe? F decreases, but V increases. At the mean position, what happens? At the mean position, y will be 0. So V equal to omega A. This is maximum velocity. This we refer as V max. And acceleration is what? Acceleration becomes 0 because F is minus omega square y. At the mean position, y is equal to 0. So particle's acceleration is 0. So what will happen? Particle will stop over there. Isn't it? No. It will never stop. Why? Because it got maximum velocity here, V max. Due to inertia motion, it continues its motion towards left. So from the mean position, from O to B dash, what is happening? From O to B dash, due to inertia of motion, particle continues its motion and then V equal to 0 at B dash and acceleration becomes minus omega square. So particle was going this way, acceleration directed this way. Okay? So again it turns back. Start moving towards O. Okay? So and this process repeats. In nature, whenever other forces are absent and a particle describing this kind of motion will be referred as simple harmonic motion. Okay? And simple harmonic motion, the most important characteristic is acceleration proportional to displacement and directed towards the mean position, directly proportional. Now, now we'll see some phenomenon in nature which can be explained, and the time period of the simple harmonic motion, the resulting motion will be SHM, can be studied nicely. So first example we take vertical motion of a spring. So why not horizontal motion? In both the cases, vertical or horizontal, I am saying it will perform SHM. At present, you neglect G. Neglect gravity. Okay? Before we start setting this example, vertical motion of a spring, I'd like to say that you have to get a particle in UCM to explain SHM. By now, do I need to consider that particle should be in uniform circular motion, then another particle will perform SHM? No. Now SHM becomes independent topic. Okay? Simple harmonic motion independent. Why independent? Then you will say that you have borrowed omega from UCM. Why are you saying this is independent? It is independent because we will remember this manner, that particle has a time period now, t equal to 2 pi by omega. This time period, if the particle starts from here to go there, to come back, continue here, and then to go back here, the time required will be the time period. O to B, then B dashed, then 2. This is time period. This time period is 2 pi by omega. We have borrowed from SHM, but now T is a well-defined term. Some time is required. Some time is required to perform this oscillation. You'll say that then why omega? There is no angle described here. Then we'll remember we have borrowed the term omega from uniform circular motion. Please don't be confused. Simple harmonic motion now independent topic. It has a fixed time period. Omega, if people ask, if you face in a problem, we will say, otherwise we will remain silent. Our time period matters. An equation of simple harmonic motion also. Okay? And when the particle performs SHM, I just told you that we need not bring the circle of reference. Then question is, how the particle start SHM? How do you say that? Particle was at rest. You are not taking particles motion in circle, then you are saying. My answer is, whenever, please remember, whenever you are going to prove a motion SHM, you disturb the particle slightly from the equilibrium position. From equilibrium means from mean position. Suppose particle will perform oscillation here. We don't know whether it will be SHM or not. We are going to prove that for small displacement, the motion will be SHM. So who will give the displacement? If you don't take the help of UCM, then we have to give the displacement. We have to displace the particle slightly from mean position. Calculate the restoring force. If you find restoring force proportional to displacement, then motion going to be simple harmonic. Okay? So I told you that both vertical and horizontal motion, neglecting gravity, will perform SHM. Here I am taking a particle or a mass attached at the end of a spring. Okay? Spring is resting on horizontal surface. Okay? It's K. K is the force constant. K is the force constant of the spring. And suppose a mass M we have attached here, and it is resting on horizontal surface. This particle of mass m tied at the end of a spring of force constant m is resting on horizontal surface which is frictionless. We pull aside or we compress the spring. If we take the spring, if we take the mass towards right, if we move it towards right by a distance x, this one x, then what is the restoring force developed here? Restoring force, you have given displacement this way, restoring force F is going to be what? K into x. So what will be the acceleration? But this force towards left, we put a minus thing over there. Restoring force, opposite to displacement, minus this. So acceleration going to be what? Acceleration is F by m. K by m into x. Okay? So we have got a proportional to x, therefore motion is SHM. Okay, how do you calculate the time period of this oscillation? Now, F is what? Minus omega square x. So, omega square k by m. Omega equal to root k by m. Time period is two pi root over m by k. This is the time period of the particle in SHM. Okay? That time period is well defined term. We have got everything in terms of time period. Now, we can consider the second example as the motion of simple pendulum. Will it perform SHM? This is also going to perform SHM. How to prove it? Pendulum is there. This pendulum is suspended at the end of a light string. Its length be L. Mass of the bob be m. This is weightless, inextensible string. Will disturb the particle slightly from the equilibrium position. This is obviously equilibrium position. Question arises, till what angle we can disturb the particle? My answer is small angle. Why small angle? That I will explain. If the angle is big, we won't be able to prove it. Motion SHM. Okay? So this actually belongs to the category of mechanics of small oscillation. You can refer the whole chapter that way. It is mechanics of small oscillation. It is disturbed slightly, okay, from the equilibrium position. It is better you draw the circular arc on which it travels. It will be like this, no? It will be like this. Horizontally also it is disturbed. If we say that this is the displacement angle theta and theta is small, then there is no difference between arc length and this horizontal displacement. If this is equal to x, then for small angle theta, we can write x equal to L theta, that S equal to R theta. That you can write. But here what I told you, every time you have to calculate the restoring force. What is the force acting on the mass? That mg acting vertically down. Okay. So the restoring force you have to calculate. A component of mg going to be restoring force. For small angle theta, this force also directed towards the equilibrium position. If this one theta, this is going to be theta. Here the component is mg cos theta and this one mg sin theta. So the restoring force will be what? Minus mg sin theta. Why? You have disturbed the particle for small angle. For small angle theta, we can say that sin theta approximately equal to theta. Isn't it? That we know very well. So, the restoring force is minus mg into theta. Acceleration of the particle will be what? Acceleration of the bob F will be what? Minus mg into theta by m. G into theta. Minus g into x by L. So F will be minus g by L into x. This you write minus omega square x. Omega square is g by L. So omega will be root g by L. Time period will be 2 pi by omega, that is 2 pi root over L by g. So these two motions, their formula for time period, you should keep in your mind to solve problems based on it. But these are the simple examples I am giving you now. Another example let us consider. Because fluid you all must have completed. With the help of that buoyant force acting on a particle, we are going to prove another motion SHM. Which one? Let me show you. Third example, example 3, that oscillation of a cylinder immersed in a liquid. The liquid, there is a cylinder, this is the cylinder, this is floating here in a liquid. Density of the liquid is known. If the cylinder is pushed inward slightly and then left, then the motion will be simple harmonic. How the motion is simple harmonic, that we are going to prove. Okay? Imagine length of the cylinder be, let L equal to, or you take LL, L be the length of cylinder. Rho stands for density of cylinder. And sigma stands for density of liquid. Okay? Particle is disturbed slightly and then released. Every time slight disturbance. Because huge disturbance will create huge problem for you. Remember, in this mechanics of small oscillation, proving calculation, actual motion of SHM can be realized if you give small displacement. Sigma stands for density of liquid. This one displays, another thing you consider, A be the area of cross section of the particle in SHM. Okay. Now, if this one displaced slightly, suppose the length submerged be L0. L0 be the length submerged. If the cylinder pushed downward slightly by a distance x, then its motion will be SHM. Then its motion will be, and left. If it is pushed slightly downward by distance x and then released, you must add it, and then released, it can be proved that its motion means what? The vertical oscillation. Vertical oscillation is SHM. Why? Before I derive it, I just tell you why. Initially it is floating in the liquid. So, you know the principle of flotation. It floats because upthrust equal to weight. Upthrust and weight are balanced. Initial length submerged here, we have taken L0. So, when pushed downward by x, increase in buoyant force will be what? L0 plus x into area into sigma g is the new one. Okay? That minus, initially it was L0 A sigma g. So this is going to be x A sigma rho g. How do I write restoring force? Because you have pushed downward, restoring force opposite direction. We will take restoring force negative always. Restoring force is what? Restoring force going to be minus x A sigma into g. Restoring force. So acceleration will be what? This is F by m, you know, minus x A sigma g. What is mass? Area into length into rho. Clear? So this is going to be minus sigma into g by L into rho x. F. But F equal to minus omega square x. So omega square sigma g by L rho, omega will be g sigma by L rho. Time period will be what? Two pi by omega under root sigma g by L into rho. Clear? This way you can get time period. Remember this basic principle always. Never forget the basic concept. In this chapter, what is the basic concept? Basic concept is that to prove SHM, will displace the particle slightly from its equilibrium position, then calculate the restoring force, then acceleration going to be proportional to displacement. Then motion is simple harmonic motion. And 3 standard cases I have proved. So let us see some numerical problem in the next lesson. Okay? T equal to 2 pi into her omega. So this will go up. L rho by G sigma. This will be L rho by G sigma. Clear?